All right, exponential functions. Okay, so just like with exponential equations, the exponential equation is an equation where you had variables located in the exponent. Same thing with exponential functions. So it's a function whose equations contain a variable in the exponent. Now, when you take some of your science classes, you're going to notice that some of the functions are exponential. Like you deal a lot with exponential growth and decay. So any situation that increases rapidly or decreases rapidly can be modeled using exponential. When you talk about earthquakes, those are modeled using logarithms. But if something is increasing rapidly, you can see what the graph looks like in that case, or if something's decreasing rapidly, then that's modeled using an exponential function. So sometimes a population of a country can be modeled using an exponential function. In that case, the variable will be located where? In the exponent. But here's the definition of an exponential function, though. All right, so we're going to say this. We're going to say that the exponential function and we'll call it f, like f of x, g of x, h of x. So we're just going to call it, in this case, f. So the exponential function f with, now yesterday when we were talking about exponential equations, and we solved those exponential equations, we made sure, and that's the only way we knew how to do it, we had to get what to be the same? The basis. All right. So the exponential function f with base b, so I just want to make sure you remember the word base, with base b is defined by, and here's how it's going to look, f of x equal b to the x. F of x equal b to the x. Notice that's an exponential function because where's the variable located? In the exponent. Now remember, f of x stands for what though? Y. So we could say y equals b to the x. Now that idea here is going to be important when we start talking about logarithms. Okay, now something else you gotta remember about b. So b must be positive. You'll notice that whenever we're graphing exponential functions or doing anything with an exponential function, the base is never going to be negative. If you go back to those equations where any of the base is negative, yeah, none of the bases were negative. Because in an exponential function, exponential equation, the base cannot be negative. The base must be what kind of number? Positive, and it cannot be this. And it can't be 1. It could be any positive number but what? 1. And you're going to see why as we go through this. You may say, well, why can't it be 1? You'll see. So it looks like this. So we'll say b must be positive, meaning b has to be bigger than 0. And b cannot equal what? 1. Now don't say b is greater than or equal to 0, because b cannot be 0. B has to be what kind of number? A positive number. So anything bigger than 0, but not being 1. And x, though, can be any real number. So is it okay for x to be negative?
Yes.
Yes. When you solved those equations yesterday, did we get any of those x's to be negative? Probably. Yes. So x can be any real number, but the base cannot be any real number. The base has to be what kind of number? Positive, but not 1. So examples of exponential functions would be something like this. F of x equal 3 to the x. G of x equal 1/3 to the x plus 1. H of x equals 4 to the x plus 2. K of x equals negative 3 to the x. Those are all examples of exponential functions, because what do you notice about the variable? It's an exponent. Now, some of you may say, well, I thought you said the base can't be negative, right? You may, so K of x may cause some of you a little issue. What's being raised to the x power? 3. Not negative 3. We talked about this in previous courses. If I wanted negative 3 to be raised to a power, I'd have to put it where? In parentheses. That's not in parentheses. So again, what is the base in the function k of x? Is it 3 or negative 3? It's 3. Now, when we start graphing these, you're going to see what that negative does. What does negative do to a graph that looks like that? So we're going to see what that looks like. Okay? All right, so let's start graphing some of these. All right, so on the big grid paper, and I want you to use the big because we're going to graph 3 things on it. So the first thing I want you to do is to write this down. So we're going to graph each of the following. Okay, number 1, I'm going to give you 3 functions. I'm going to write down 3 functions, and we're going to graph each one separately. So f of x equal 2 to the x, g of x equal 2 to the x plus 3, and h of x equal 2 to the x minus 5. So in all cases, what do they have in common? The base raised to the power, right? 2 to the x, 2 to the x, 2 to the x. So h of x is 2x minus 5. All right, so let's concentrate right now, though. Let's concentrate on that first one. And let's talk about how to graph the first one. All right, we're going to talk about this using a t-table. Remember, what is the domain? What's the domain? What's the domain? If I ask you to tell me what the domain is, what are you going to say? No. I don't say the x-axis. What do you say? It's a set of x coordinates, but what is it, though, guys?
The limits.
1.
You tell me that the x value is only 1?
Oh, you mean of that?
What is the domain of that function? Negative infinity to infinity.
Oh, okay.
Any real number, right? Didn't we say that in the definition that x can be what? Any real number. So what is my domain? Negative infinity to infinity. And the reason I asked you that was because I wanted you to tell me what could I use for x. And I wanted you to say, well, you could use anything for x because we just learned the definition of exponential function. The domain is what? Any real number. Any real number.
You were hoping for a lot.
Yeah, I was hoping for a lot. It's okay. It's all right. Now you know. So give me a number for x. What's always a nice number to use for x, though?
2.
0. In fact, when I let x be 0, what is it that I'm finding?
2 to the 0 power.
What is it I'm finding when I let x equal 0?
Y.
The y what? Y-intercept. You just had a worksheet on that a while ago. To find the y-intercept, you let what? X be 0.
2 different things.
So when I let x be 0, and in all of these, you're going to let x be 0. When you let x be 0, you're actually finding what? The y-intercept. Stop saying the y-coordinate. I need you to say the y-intercept.
Y-intercept.
Thank you. The y-intercept. So let's go ahead and let x be 0. All right? Now, do not use your calculator on this, because I want to see if you remember something. So when I let x be 0, I get 2 to what? 0. Let's see if you remember something from yesterday. It is 1. Very good. You kind of redeemed yourself a little. At least you remember. At least you were able to connect that. And if you actually use your calculator and you put 2 to 0, you're going to get 1. So I have the point 0, 1. So if you want to start plotting that, you can. So let's go ahead and plot that point. So at the point 0, 1. So that's right here. All right, now let's go ahead and let x be 2. What you want to do with some of these situations is let x be positive numbers and let x be negative numbers. So let x be 2. See what happens. If x is 2, because remember the domain's any real number, right? Negative infinity to infinity. So when x is 2, I get 2 to what power?
2.
Second, which is what? 4. So I get 2, 4 right here. If x is, let's say, 3, I get 2 what?
8.
Cubed, which is 8. 3 8s right here. Now don't think that's a straight line. Exponential functions are not linear. What kind of functions are the graph is a straight line? A linear function. Is that a linear function? Those are exponential functions. A while ago we said exponential functions rises rapidly or falls rapidly, decreases rapidly, increases rapidly or decreases rapidly. So it cannot be a line.
What's the term for that kind of shape?
There is none. We just say it's exponential function. If x is 4, and I think I have enough space here. If x is 4, I get 2 to the 4th, which is what? 16. So I'll plot the point for 16. I want you to notice something. You see the idea of rising rapidly? So when I start connecting just that first one with the others, it looks like this. I do the best you can with withdrawing this, but my graph is rising rapidly, right? Kind of like this. See how it looks? Now, you're not done with this because all I've done was use positive numbers, but I also have to use what? Negative numbers. Now, that's where you have to listen to the discussion. And this is also where you're going to need to use your calculator. If x is negative 1, if x is negative 1 on your calculator, what's 2 to the negative 1 power? 1/2, right? 0.5. So I'll plot the point, negative 1, 1/2. I want you to notice this. Negative 1, 1/2 is right here. And so just start connecting like this. Start connecting. Don't go any further. Stop at that when you connect that point. Let's do another one. Let's say x is negative 2. I want you to notice what's happening, guys. When x is negative 2, use your calculator. When x is negative 2, I get 2 to the negative second power. What decimal is that? 0.25. 0.25, right? So negative 2.25 is about here, right? Y'all see this? Connect it. But it's got to be a curve. Don't make it a line. Don't make it straight. It's a curve. If x, let's say, is negative 6, negative 6, what's 2 to the negative 6 power?
Is,
0 what?
15625.
Wait. Slow down. 0 what? 0.16?
Well,
0.016, okay. 0.016, right? So we're approximating here.
yeah.
But here's the point I'm trying to make. My y values, look at the y values as we're going to the left. My y values are getting smaller and smaller and smaller, aren't they? And here's the other thing I want you to see. Are any of my y values, look at the t-table, are any of my y values negative?
Nope.
They're always going to be what? Positive. They're always going to be positive. So when I graph this, and let me ask you this, where in a coordinate plane are your y values negative? Where are the y values negative in a plane? Below the x-axis. So here's my question. Will that graph ever go below the x-axis?
No.
Why not? Because your y values are always what kind of numbers? Positive. For this function, it's positive. Will y ever be 0?
No.
No. So will it ever touch the y-axis? I'm sorry. Will it ever touch the x-axis? No. So what happens is this. Your graph is getting closer and closer and closer to the x-axis without touching it or crossing it. And that's all you do. You're done. You graph this. Now, you see how I went to the left and I said the graph's getting closer and closer and closer to the x-axis? I said the x-axis, right? So that x-axis is called, here's a new word for you. Yeah, you may want to listen. What kind of, now I'm going to ask you this, is the x-axis horizontal or vertical? Horizontal. So an exponential function, all exponential functions have what's called a horizontal asymptote. Now, I did not say what you think I said.
You might want to spell that out. You might want to spell that for us.
So all exponential functions have a horizontal. So what I mean by horizontal is your graph, one part of your graph is going to kind of level out. And so if I were to keep on going, it would look like this would be a straight line, horizontal line, wouldn't it? But it did not, because it cannot be a horizontal line, because remember, a horizontal line's constant. These y values are not constant, they're getting smaller and smaller and smaller. But it's going towards a horizontal line. That horizontal line is called a horizontal asymptote. Asymptote.
Asymptote. Asymptote.
Horizontal asymptote. So if you want to abbreviate, you can just say HA. HA. All right? So in this case, I want you to look at the graph that we just did. In this case, what is my horizontal asymptote? What is my horizontal asymptote? The x-axis. We just talked about that. Your graph's getting closer and closer to the x-axis. So your x-axis is the horizontal asymptote. So listen carefully. Your horizontal asymptote. All right, now listen how you're going to write this. For this exponential function, the horizontal asymptote is the x-axis. Remember, we said that all exponential functions have a horizontal asymptote, right? Mm-hmm. Depending on the function, though, the horizontal asymptote is not always going to be the x-axis. It's easy to determine, though. You'll see the next one we do, you're going to see what the horizontal asymptote is right away by looking at it. But when drawing the horizontal asymptote, you're going to use a dotted line. So keep that in mind. We're going to talk about that, a dotted line. So this horizontal asymptote here is the x-axis, right? So you see I'm kind of drawing a dotted line right here to represent the horizontal asymptote. You'll see that? To put a dotted line on the x-axis, kind of like this. So that's going to represent the horizontal asymptote. Now, what kind of line is this horizontal? What kind of line is the asymptote? Horizontal. Now think about what we did before the first part of the class. A horizontal line, a horizontal line only has one variable. What variable is it? Y. Okay. So I'm going to ask you this. If I draw this horizontal line right here, in 2 seconds, you better tell me what that equation is. Well, maybe 5 seconds. Y equals 6. In 1 second, you better tell me what this equation is. No, y equals 3. Half a second. No, y equals -4. So when naming a horizontal line, it's always going to be y equal, right? And notice that in each of these cases, that number you use is where the graph crosses the y-axis. So let's go to the x-axis now. You cannot make a connection, girl. Come on. These are not x's, these are what? Y's, right? So this x-axis, what is the name of this x-axis? Y equal what? Very good. Y equals 0. This is y equals 0. Now you know that the x-axis can also be called what equation? Y equals 0. It's a horizontal line that crosses the y-axis where? At 0. The origin. So when you tell me, on the worksheet it'll say HA. So you're going to say, now this is how you're going to say it now. You see how Alicia kept saying 6, 4, and I kept saying no, no, no? Why did I kept saying no, no, no?
Because you wasn't doing the Y.
She wasn't doing the y. Okay? So you're going to say the horizontal asymptote is y equal what?
0.
0. Y equals 0. So don't say 0, you got to say y equals 0. Which axis? The x-axis. And there's your graph. So you graphed f of x equal to the x. And you also told me what the horizontal asymptote is. What was the horizontal asymptote? Y equals 0. You also told me, although we kind of had to get to it for about a minute, but you also told me what the domain is.
Oh, negative infinity to infinity.
In fact, all of those exponential functions, what's going to be the domain?
Negative infinity
Negative
to
to
infinity.
infinity. From the graph, you can tell me what the range is. Remember, range goes from bottom up? What's the range?
0.
0 to infinity. Now remember, when we talk about domain and range, sometimes you have to use the brackets. Am I going to use brackets here?
No.
No, because does y ever become 0?
No.
Does the graph ever touch the x-axis? So the range, if you look at it, remember you go from bottom up. Where do I start touching the graph? On the x-axis, although it really doesn't touch it, so that's why I use parentheses. So I go from 0 all the way to what? Infinity. All right, so that was the first one. The next one's going to be a little bit easier for you because you have the background now. So listen to the next one. Now listen carefully. The next one was the 2 to the x plus 3. And I want to graph this on the same coordinate plane. Yes, same coordinate plane. Same graph. So I purposely made the main part of the function the same, 2 to the x. The base is 2, the exponent is x. The only difference is that this says plus 3. Listen carefully. This said plus 3, and this said plus what? 0. So I said that plus 0? That plus 0. Why does he keep emphasizing plus 0? What do you think that plus 0 represents? What do you think that plus 0 represents? The horizontal asymptote.
Oh, so 3 is going to be your
So
horizontal.
y equals 3 is going to be the what?
Alrighty then.
Horizontal asymptote.
Good job.
Yeah, I should get a award.
Well, you're kind of redeeming yourself a little bit. So y equals 3 is going to be the horizontal asymptote. What's going to be the horizontal asymptote for function h? Nope, not -5.
Why?
Y equal -5.
I missed it.
That's to be the horizontal asymptote. So now you know what the horizontal asymptote is. It's that number attached to the base tracer power. Yes.
Is that number always, the attached number always going to be the, like, y equals 3 or y equals -5 is always going to be the horizontal asymptote?
We can talk about that. Yeah. That was our discussion a while ago. So when we graph this, when we do the t-table, you're going to see that the graph's going to get closer and closer and closer to what y value? 3. So again, the horizontal asymptote will be y equals 3. All right? So let's do a t-table for that one. What's a nice number to use for x?
0.
When I let x equal 0, what is it I'm finding? The y-intercept. So when x is 0, I get 2 to the 0 plus 3.
1 plus 3.
2 to 0 is 1. Good. 1 plus 3 is 4. So, and that's going to be your y-intercept. All right, so I'm plotting the point 0, 4, which is here. Okay. Give me another value for x. 2, 1, let's do 1. If x is 1, I get 2 to the 1 plus 3, which is what?
5.
Which is 5, right? So I'll plot the point 1, 5, which is about here. If x is 2, I get 2 to the second power plus 3, which is 4 plus 3, which is 7. So I plot the point 2, 7. If x is 3, I get 2 cubed plus 7, which is 8 plus 7, which is
11. 8 plus 3.
oh, I'm so sorry. I was looking at this right here. 8 plus 3, right? 11. So 311. And then notice that if I start connecting those, it also rises what? Rapidly. Now, what is a horizontal asymptote?
3. Y equals 3.
Y equals 3. Now, at that point, and even before you start doing that t-table, it's a very good idea to draw your horizontal asymptote. So even before I start doing any of that, I should have, or I could have, drawn the horizontal asymptote. Now remember, when drawing the horizontal asymptote, it's going to be a solid line or a dotted? Dotted. So your horizontal asymptote, the horizontal asymptote is y equal what? 3. So on y equal 3, right here, I'm going to draw a dotted line. So that's my horizontal asymptote. And guys, once you get to that point, you know what's going to happen. If I start using negative values for x, then, and let's just do that. Let's do one of them.
Flatten out.
Let's say negative 1. If x is negative 1, I want you to do this in your calculator. If x is negative 1, on your calculator, you're going to say 2 to negative 1 plus 3. What's that? 2.5. So negative 1, 2.5 is here. I want you to notice, based on what we talked about in the previous one, negative 1, 2.5. See how it's getting closer and closer to what? Closer and closer to what? The horizontal asymptote.
Something didn't work out right. Hold on. I got 3.5.
I'm sorry, 3.5, excuse me.
We got one up there.
Yeah, 3.5. But I plotted 3.5. I just said 2.5. See how it looks? You're done. You just have to know the fact that at one part of the graph, it gets closer and closer to what? The horizontal asymptote. There's your graph. You're done. See how much quicker it is? By just knowing something about horizontal asymptotes, and at some point the graph gets closer and closer to it without crossing it. What's the domain?
Negative.
All real numbers, negative infinity, infinity. The range is what?
3 to infinity.
3 to infinity. And you're done. That's how simple this is. Now, there's more we're going to do with this, but those are the basic idea. Okay, so that was the basic idea. There's some more we're going to do with this, but keep in mind we're going to continue with this the second part of tomorrow. Keep in mind about the horizontal asymptote the domain is all real numbers, and the range is from that asymptote to infinity. Now, everyone we've graphed so far, where was the graph located, above or below the asymptote? Above. Is it always going to be above? You got to say no. So there are situations where the graph's going to be where? Below. And we're going to talk about that tomorrow. Okay? All right, so let me see if, well, here's what we're going to do instead. For the 7 minutes we have left, start working on that worksheet that's due tomorrow.